Who is Cheung, and what is it about? Formalized Burrows-Wheeler transform. Just need the slides, and then we're ready to go.
Hello? All good? Cool. Hi, everyone. I'm Lewis, and so today I'm going to present our work on formalized Burrows-Wheeler transform. So a big thank you to my supervisors, Alistair and Christine, who helped me complete this project. So the structure of this talk will be as follows. First, some just general motivation of why did we want to formalize this transformation? And then just a very brief overview of what the actual contributions of the paper, of what we actually did in the paper. And then a more in-depth dive into what the BWT is and sort of how is it formalized. And then some just key properties about it which are necessary to understand its inverse transformation and a little bit of its formalization. And then just some concluding remarks. So without further ado, the motivation. So the motivation of this was, I thought the Burrows-Wheeler transform is a very cool transformation. But to convince other people to actually want me to do this project, the reason is that the Burrows-Wheeler transform is this invertible data transformation that what tends to permute sequences so that they have long runs where there's only just a few distinct symbols. In addition, has a one-to-one correspondence with the suffix array, which is a data structure that is very useful when we're talking about pattern search applications. And so because of these two, it is widely used in data compression and also text search. Maybe you might have heard of some of these examples, maybe not, but here's one such example, which is bzip2, which is one of the standard file compression softwares on most computers. And essentially what it uses the BWT for is as a basically one phase to boost the compressibility of the data. Another tool, which is a bit more domain specific, is a tool called Bowtie2, which is a genome sequencing tool, which is widely used in medical research and diagnosis. For this particular tool, the Burrows-Wheeler transform is used to transform a DNA sequence so that it can be both compressed and searched at the same time. Now, these are just a few examples, but there's plenty more. And also, there's a lot of literature about using the Burrows-Wheeler transform and analyzing it. And so because of this, it's quite important that we have efficient and correct ways to actually compute it. But if we want to be able to actually do that properly, we probably need to have a deep understanding of how does it actually work, which leads on to why we actually, or what we actually did. So, considering that I'm here speaking to you today at a conference about certified programs and proofs, naturally that means, or most likely, formalization. And in this case, what we did was formalize two different approaches to construct the Burrows-Wheeler transform. The first being its canonical construction, which is how it is described in its original paper, and also an alternative construction using suffix arrays, which allows it to actually have a linear time construction time, because what you can have is a linear time suffix array construction algorithm, and then from the suffix array, build the Burrows-Wheeler transform in linear time. So with those two constructions, naturally you want to prove equivalence, that is that they both produce the same result. And then building on this, we then want to prove key properties about the BWT so that we can actually then verify that it is invertible. And in this case, what we do is actually verify a linear time inverse, which, although albeit it does use some pre-computed data structures, but they themselves can be also computed in linear time, so not affecting the time complexity there at all. Now, all of this is formalized in Isabelle, and as far as we are aware, it is the first formalization in a theorem improver. So that's what we did in the paper, and so now a bit more on actual Burrows-Wheeler transforms. I haven't really gone into detail about it. So the way that I'll explain it is through an example. Consider a sequence, yada yada dollar, where the dollar symbol just marks the end of the sequence and is treated as the smallest symbol in the alphabet. We sometimes also call it the sentinel. And the reason why we need to do this for sequences which we pass to the Burrows-Wheeler transform is that we need that symbol so that we can actually do the to invert the result. But more on that later. So given such a sequence, how do we actually construct the Burrows-Wheeler transform? Well, what we do is first, we generate all of its rotations. And in this case, there are 9 distinct rotations. The exact ordering of these doesn't really matter because in the next step, what we do is actually sort these in dictionary order or lexicographical order. And so we end up with this, so recalling that the dollar is treated as the smallest symbol, and hence that's going to be our first rotation, and so on from there. And then the last step is to take the last column. And this last column is the Burrows-Wheeler transform, and we only need this to get back to the original sequence. And what you can see is that it does tend to group some similar symbols together. Now, this is a very contrived example, very small, and doesn't really show what the Burrows-Wheeler transform is actually capable of. So here's a slightly larger example. Consider the abstract to our paper, which is standard human text. Then you pass it through the Burrows-Wheeler transform, and you get something which no one can read. But what you can see is that it has grouped similar symbols together. So for example, you can see all the capital W's are grouped together, and then in some lines, you can just see like a whole like section on N's, and then maybe T's and so on. And because you get this type of output, it naturally means that it's very nice for data compression, especially because this is invertible. So we can get back the original. So that's sort of the Burrows-Wheeler transform at a high level. And that's what this sort of high-level algorithm basically says. And to convert this into something like Isabelle, which in this presentation, I'm not actually going to show any Isabelle code, but sort of like a more mathematical stylized version of it. What we do is model sequences as lists. And so we then can use Isabelle's inbuilt list functions, such as rotate to rotate lists, sort to sort them, although we do have to instantiate the ordering with lexicographical ordering, and also last to just take the last element for the list. Now, strictly speaking, our definition, we purposely make it total so that we don't run into all those other issues because of it being a partial function. But when we actually do proofs about its correctness and other properties, we do need to pass around a predicate which just says that it's terminated by this special sentinel symbol. And that's what the valid thing is for. So that's the canonical construction as how it is presented in the original paper, and as shown in many sort of, if you're learning about this transformation, that's how it's normally presented. Now, moving on, you can also construct it using an alternative approach using suffix arrays. And to see how that comes about, let's go back to the earlier example and consider the sorted rotations matrix of that sequence yada yada dollar. Now, if we ignore everything after the dollar symbol, what you can see is that we have the suffixes of yada yada do. And not only that, these are all in sorted order, which naturally leads to the suffix array. Now, strictly speaking, the suffix array is only the thing on the left, which is just the suffixes in sorted order, but they are represented by their locations into the original sequence. So using that plus the original sequence, one can obtain that sort of rotations matrix, which then mean that you can obtain that last column, which is the Burrows-Wheeler transform. Now, we don't actually need to compute that whole rotations matrix. We can just use a function like this, which simply uses the suffix array to find that last column. And to do that, you simply subtract 1 from it and look up what the value is there in the original sequence. Because the idea is that the last column is simply represents the symbol that occurs before that suffix. Now, there is one edge case, which is when we're talking about the suffix array value when it's equal to 0, which is basically the 0 suffix, because in that case, it's the whole sequence. And so when we look at the sort of rotation matrix, that's not going to be the last column is not going to be the symbol before, but simply just the last symbol in the actual sequence, as is shown in that piecewise function. So that's how you would construct it using suffix arrays. In our formalization, what we do is something a little bit different, which still achieves the same result. So the first thing is that we actually build on some previous work where we formalized a linear time suffix array construction algorithm, but we don't actually use any of that part, but simply the axiomatic characterization of what a suffix array construction does. And that's that SA part in that definition. And what we do then is also, instead of using that piecewise function, we use modular arithmetic. Now, for those who are a little bit more eagle-eye, you can see that we have to add an additional value, which is the length, so that we don't run into this issue because we are dealing here with natural numbers where you have 0 minus 1, which can lead to problems. So we add the length value before we do that so that we don't ever run into that issue. And that's the construction using suffix arrays. Now, it's sort of, are these equivalent? And this is quite straightforward because essentially what we do is show that suffixes are just prefixes of rotations, and they have the same lexicographical ordering. And because of this, the construction using suffix arrays will actually construct that sort of rotations matrix, but implicitly. And so you show that since both of them construct the rotations, sort of rotations matrix, they both will actually extract that last column, which is the Burrows-Wheeler transform. And so that's the forward direction of the Burrows-Wheeler transform. Now, onto some key properties that we need in order to talk about index. So to do that, we'll go back to that sort of rotations matrix. I know it's starting to get a little bit more repetitive at this point, but we'll spice it up here right now. So what we do now is augment it with augment each symbol with its location in the original sequence. And that's sort of to make each symbol sort of unique. Then we also want to ignore basically the center part of that matrix. So only consider the first column and the last column. And with that, we can start talking about the key properties. The first one is fairly simple, which is the first column is just the last column. Now, this follows simply because the first column is the first symbol in the sorted rotation matrix, so that has to be all in sorted order. And the other thing is that each column is a permutation of the original sequence. And so that's why this property holds. The next one kind of relates back to that whole suffix array construction, which is that the ith value in the last column precedes the ith value in the first column, except for that one special case. So in this case, you can see that y0, which is in the last column in that fourth row, should precede a1, which is in the first column. And the final property is that the relative order of equal value symbols is the same in the first column, the last column. So for example, if we just consider all the A's, what you can see is that we have this ordering A7, A5, A1, A3 in both the first and last column. Now, the interesting thing about this is that if we know the position of where one of these is in the last column, we can easily obtain its position in the first column. So for example, if we know that A5 is the second A in the last column, we can figure out that it must also be the second A in the first column. The other thing is that we know the general region where the A should lie because they're all in sorted order. And because of this, we can find out its location. And we call this the LF mapping because it maps the item from the last column to the first column. So just a bit more for this property about why it's actually true. Consider the suffixes starting with A. Now, the ordering in the sorted rotation matrix does not depend on the first symbol, as these are all equal, but rather on their suffixes. And since these must be in sorted order, they will have that same ordering in the matrix, which then means that the A's will have that same ordering in the last column. And essentially, for all those properties, we use those sorts of arguments, except instead of using the annotations of this locations in the original sequence, we actually talk about suffixes instead, because there's a one-to-one correspondence there instead. And that's a lot easier to deal with. Anyway, moving on. Now we have all the ingredients to actually be able to talk about the inverse. So, again, consider the sequence ADY, YD, AA, $, which I think most of you will have realized this is just the Burrows-Wheeler transform of yada yada $. But how do we actually invert this? Well, we can use the first property to actually obtain that first column simply by sorting it. Now, you can do this using a linear time. For constant size alphabets, you can use something like counting sort, and this is then in linear time. Then we reconstruct the original sequence in reverse order, starting at that one unique symbol that we know, which is that sentinel, which is, in this case, $. And so starting from there, we can then apply the LF mapping, or just simply go to the first position in that first column, because we know that's going to be the smallest symbol, but doesn't matter which one you choose. So we use the LF mapping, and then we can use property 2 to find the preceding symbol in the last column, which is A7. And then we do the same, where we apply the LF mapping to find where that A7 occurs in the first column, and find its preceding symbol, which is D6. And we essentially just keep repeating this until we have a sequence that is either of the same length as the BWT-transformed sequence, or until we reach back at that sentinel. And that's the inverse. Now, in terms of how do you actually write that in terms of an algorithm, that's what it looks like. I'm not going to go into detail about it. But essentially, when we formalize this, we sort of split it up into three key parts. The first being that LF mapping, the second being that repeated application of that LF mapping and finding of the preceding symbol. And the last part is just basically a wrapper so that we can start at the unique last symbol. And also only do the repeated application n times, where n is the length of the original sequence, or the BWT-transformed sequence. With that, naturally, we want to show that there's actually. And so we have a very simple theorem to prove, which is if you have a sequence and you transform it with the BWT, and then you apply its inverse, you should get back the original. And the way that we prove this is first we prove that the LF mapping is correct. And so essentially, that argument boils down to showing that the ith symbol is the ith symbol in the ith symbol in the last column is the ith symbol in the first column. But specifically, what we do is actually say that using the indexes and talking about the suffixes, if you look at the suffixes starting with those letters in the last column, and then looking at the suffixes as they are in the first column, you'll see that their relative orders will be the same. And because of that, then it follows that the symbols also are matching there. Then the next part is to actually prove that applying this iteratively and using the second property to find the preceding symbol actually produces the sequence, the original sequence. In this case, what we actually do is prove stuff about the indexes of the symbols, so their locations, how they map, where they map to, essentially. And so what we try to show is that if you apply this sort of inverse permutation on the locations to the permutation you would obtain if you applied BWT, what you should get is this subsequence from 0 up to n, which could be rotated. And then once you have that, you can then show that if you start at that unique last symbol, then you also apply the correct number of times, you should get the sequence from 0 up to n, and from this you then obtain that you've got actually the inverse. Now, to actually prove all of this, what we did was actually split up the proof into sort of two parts. We proved that all this is correct for some abstract version where we say abstract, meaning that it has additional information about the original sequence and the suffix array. And so that just makes life a lot easier so that we can actually use additional properties about suffix arrays and actually know what the exact values are. Then we do a refinement to actually eliminate all of that information so that now you only have reference to the BWT-transformed sequence. And then you get the proof. And so, in conclusion, what we did was formalize two different BWT constructions and prove that they actually do produce the same result. And then we formalize some key properties about that sort of rotations matrix, which are necessary for the correctness of its inverse. And then finally, we verified the inverse itself. So some future work that we are interested in looking at is a formal complexity analysis, because at the beginning I mentioned, okay, these are all linear time, it's great, but we don't actually go and formalize that linear time argument, which is something which is quite important, and it's probably good to have a look at. The other thing is that all these are implemented in Isabelle itself. And so if we want to actually have an implementation that is efficient, we actually want to either extract it to something like LLVM or even more efficient sort of SML or something like that, or even potentially even better is to actually go from do an implementation itself in, say, C or something, and then to verify that it is correct with respect to what we've proven here. So basically show that it refines our Isabelle embedding. And hopefully, it's as competitive as with actual real-world applications. And the final thing is that in the inverse, we did use some auxiliary data structures which are also supposedly constructible in linear time. Show that they are actually, that is indeed the case. Now, these are also very useful because they can also be used in other applications with the BWT. For example, you can actually use these to use the BWT as a text index so that you can actually search over it, like as if you were searching using the suffix array, for example. And that's it. So.
Okay, are there any questions? Okay.
Hi, thanks for the nice talk. So I just wondered, you require that your sequences are valid in the sense that they have this unique sentinel. Usually texts don't have this property. So what do you propose to treat arbitrary text? Use some option type or maybe type?
So for most texts, or if you consider stuff, for example, like C strings, they already have the null character. But in a lot of applications, they'll actually put their own sort of marker there. Or alternatively, they'll actually have an index just pointing to where you should begin your inverse. Now, we haven't shown that you can actually do the index version, so that might be a good thing to actually look at. And the other thing is that sometimes you might actually concatenate different texts together so that they have their own unique sort of sentinel, so to speak. And so that's why you can sort of have this sort of sentinel idea, because then it sort of makes things sort of as a marker for, not really for when you want to invert it, but then say, for example, if you want to just search the compressed text, that's probably more useful that way.
Thank you for the good. Thank you for the awesome talk. I'd like to ask whether there is a property about your motivation. I mean, you may use in the motivation. You said that this transformation is interesting because it puts the same characters together. Is there any probabilistic property, formal property about that kind of statement, or like it's just the observation?
Yeah, good question. So ideally, we would like to formalize something like that, but to do that, you'd having to introduce information theory, so Shannon entropy theory, and then start talking about what kind of inputs you're receiving. And as far as I'm aware, I'm not sure if Isabelle has that already formalized. If not, maybe they do, then that's something to look at. If not, then I guess we'd probably have to start from the ground up and start formalizing that whole entropy theory, information theory sort of stuff. But yes, that is probably a nice thing to actually build on this. Yes, so there are some papers which they do some analysis where if you talk about, I don't want to go into too technical, but then if you given certain types of inputs, it will have a certain characterization which you can then prove properties about how much it will compress.
Maybe a very quick last question.
Yeah.
It's more a comment than a question. The question was asked, what do you do with this dollar sign at the end? Actually, there is a variant of the Burrows-Wheeler transform where you don't need it, use it using Linden World. And do you think it would be worthwhile to implement? Or?
Yes, that's something which I hope to eventually get to. But then, unfortunately, my PhD is ending. So maybe in my free time, I'll get to do it. Or maybe if I do get a postdoc, maybe there. But yes, that's certainly something to have a look at, especially now that a lot of new research in compression actually is now starting to use the bijective version of the BWT.
All right, great. Let's thank the speaker. Thank you.